The subject of this talk today is about this small quantity, dimensionless quantity, alpha over pi, which is less than 100. And this changed the world. Here you see the two gentlemen who are very much involved in that. And in fact, Feynman is on the right side, Dirac is on the left. Talking here, he expressed, or not in that moment, but he expressed at least sometime that quantum electrodynamics, QED, is our, so to say, the jewel of physics, our proudest possession of physics. And maybe Dirac thought, well, this focus of renormalization, but in fact, Feynman himself said, shortly before he died, that he had his doubts on if this procedure of renormalization is a valid stand. And now we have tested it, and this seems to be very well established, gets better established. But still, it's worthwhile to do tests, and the tests are done in very high precision. And that's what is our speaker today has been doing, has been achieved. He has achieved enormous progress. That is Professor Gabrielse, here in maybe in Sweden, trying to state. Professor Gabrielse is a distinguished professor of physics at Harvard, and actually he got his education in Chicago at the end, the PhD at the University of Chicago, and then went to Washington, Seattle, University of Washington for a few years, and then became professor at 87 in Harvard. He has been working on different areas of trapping of fundamental particles, and one of the fundamental particles is an electron, and that's what this talk today about, which is about a new area, or opening up a new area of tests and QED.
Well, thank you very much. Well, it's a great pleasure to be here, though as in my seminar this morning, I do have at least a small complaint about your weather. I'm not really here to do physics. I was really hoping to skate from Uppsala to Stockholm, okay, which is nominally to happen tomorrow, but there's been rescheduled. But you people weren't nice enough to arrange that I have ice, okay? And I just knew in Stockholm there would always be ice. So, oh, you need the microphone? Are you having trouble hearing me back there? No? Okay, I'll put it on anyway. So anyway, but that's not really entirely fair. My wife and I have been having a good time in Sweden the past week or so. And there we are in front of the ice hotel doing our tourist thing. I also managed to take sick, but I don't think it was the response, the reaction to sleeping with ice all around. I mean, after all, it's a lot more secluded than working on a glacier. Oh, now I sound like the voice of God. Okay. Is that too loud? No. Okay. All right. And the really good news is after 3 attempts going beyond the Arctic Circle, I have finally seen the northern lights for myself. Okay. And this is actually a picture from the all-sky camera of what I saw this past Sunday night. They were really gorgeous, and they weren't supposed to be because, as you probably all know, we're at the absolute minimum of the sun activity, the sunspot cycle. Okay, but fortunately it worked out all right, so that makes up somewhat for having no ice in Stockholm, I would say. All right, now I'll get on to physics, at least mostly. And so it's we probe a single isolated electron. I like to call it a one-electron quantum cyclotron. And we've used this to make a new measurement of the electron magnetic moment and the fine structure constant. And as was, oh, sorry about that. Oh, this is a student who's very persistent, so I'll turn him off. Okay, it's wonderful the way students from all over the world can keep their professor on a short leash while you're gone. Okay, where was I? Oh yes, these are the students I was talking about, though none of them was calling. Okay, these are all people who contributed to an experiment which took about 20 years. Okay, and I must admit I never expected to work on this for 20 years. I did very much want to measure the electron magnetic moment much more accurately and thought there might be a way to do it. You can ask why 20 years, I'll get back to that in a moment, but each of these people contributed a thesis essentially. Okay, one thesis at a time. We developed the tricks that we needed, the new methods in order to make a measurement. More about that as the talk goes on. Now, you may have run into these results in the last couple of years. We published, in 2006, we published a new measurement of the electron magnetic moment. And then we also, at the same time, in the next article, published a new determination of the fine structure constant. We did it as two papers, not to pad our publication list, but because we wanted to make room for theorists, Kinoshita and Neo, to join us in the fine structure constant determination, because that's a contribution not only of our measured value of G, but also of quantum electrodynamics calculations. And so that way we could report that together. This was picked up in all sorts of different places, so you may have read it in Science or Nature or Physics Today, all of these places. And then the most recent thing is we've just submitted another paper. It's just been accepted. It's only in the archive so far that you can get it. But it's a measurement of the electron magnetic moment and fine structure constant that is more accurate by almost a factor of 3 compared to what we did in 2006. Now the question you're all wondering is, why in the world did these people take 20 years to make a measurement? I mean, isn't that what you don't want to do in physics? Well, why does it take 20 years? There are two explanations. One is Van Dyke, Schwinberg, and Daymelt did a good job back in 1987. And I think it's to their credit that they made a measurement which stood for about 20 years. That's a remarkable thing with the fundamental constant, okay? And I think it should be celebrated. The second explanation about why it takes 20 years is it takes time to develop new methods and ideas that you need to measure to 2.8 parts in 10 to the 13 uncertainty in the G value, okay? And you just can't, take someone's apparatus and polish it and do it the same way it's been done before. These folks spent a number of years trying to improve their methods, and they had sort of reached what could be done. Okay, now here are the new methods, or at least some of them. Now, new in the sense that these were things we developed over 20 years and have only recently started using together to make such a measurement. Okay, so they're new in the sense that they hadn't been used for such a measurement before. Now, the basic device is a one-electron quantum cyclotron. So we have one electron, we suspend it in a magnetic field, okay? Then we cool it so much that we see the quantum structure in its cyclotron motion, okay? Now, an accelerator physicist goes to CERN and, tries to build the world's biggest machine, right? Bigger is better. Okay, and so the LHC, it was LEP. It's 27 kilometers in circumference or something. Bigger is better. We're at the other end of the spectrum. Okay, we're going as small as possible. Okay, and the way I like to think of our system, it's really like a homemade atom. Okay, it's an electron bound to our apparatus. And what's new about this measurement is we fully resolve the quantum structure in the cyclotron and spin motion. That hadn't been done before. Okay? So, basically what we do is quantum jump spectroscopy. That is, we have the particle in one state, at the lowest state, its ground state. We put photons into our system and we see if it jumps up to the next excited state. And then we change the frequency of the photons that we're putting in and we just plot out our success. Okay? And so at concept, it's a very simple experiment. Now, in order to do that, we have to inhibit spontaneous emission. Because else, the particle, when it jumps up to the first cyclotron state, okay, would jump back down in much less than a second. And we wouldn't be able to observe that it had been in the first excited state. And so what we actually do is we put a cavity around the electron to mess with the density of states of free space. Okay, and so we actually succeed in inhibiting spontaneous emission by a couple of 100. Okay, we have to get rid of, well, we have something called the cylindrical trap cavity, which allows us to do that. I'll say more about it. That's actually a device we invented many years ago just to do this measurement. We have to get rid of black body photons, because else the black body photons would make excitations from the ground state to the first excited state, because these are in the microwave regime, okay? And so we have to get rid of those. We have a synchronized electron method I really don't have time to talk about. We have to eliminate nuclear paramagnetism from the trap, and we use something called a one-particle self-excited oscillator. If you will, it's our classical detection system that couples to the quantum system that we want to probe. Now, you can't possibly understand the details of what I just said, nor did I intend that you do. I just wanted to give you a flavor for what took 20 years, okay? Namely, each of these is about a PhD thesis, okay, to develop the method, and then we had to put these different things together. And so now, in a little while, I'll come back to these and try and make these a little more understandable. Now, if you know the history of measurements of the electron magnetic moment, sometimes called its G value, okay, you know that there are three long series of measurements. Okay, there was first the University of Michigan efforts by Crane and Rich. They took a beam of electrons in the kilovolt regime, put them in a magnetic field, so they made a cyclotron orbit as they moved around, and then they watched how the spin processed, and looked to see whether the spin would go around at the same frequency as the cyclotron motion. Okay? And that's the way the muon G-value measurement was still measured just a couple of years ago. Then at the University of Washington, the people that I already mentioned went to using one electron that was bound in a trap, and they had an experiment done at 4 Kelvin. It seemed to us that the only possible way to improve things would be to use one electron, okay, not go back to a beam. And so we use one electron, and then we have a lower temperature and a whole handful of new methods that we have added in, which allow us then to resolve the quantum structure. So what they did in sort of a mostly classical way, we're able to now do in a quantum mechanical way. That's the difference. Now, I'm used to, in my antimatter experiments, I'm used to having unusual publicity, right? Because antihydrogen experiments bring out a lot of weird people, and journalists are very interested in that. This is the Hapgood play by Tom Stoppard, where a bearded Russian physicist, okay, traps antiprotons and then is philosophical about what they mean. And how many of you have read Angels and Demons? Oh, not so many. I know there's more than that, because in the seminar I gave them this morning, I asked the same question, and I see some of the people who raised their hands not raising their hands now. Okay, so I've shamed you into not admitting that you read this, okay? This is the same author who wrote the Da Vinci Code. How many have read that? Oh, that's even worse. Okay, you should really be ashamed. Okay, but I mean, this is written about our research activity, okay, in a manner of speaking. I like to say that what Dan Brown did for the Roman Catholic Church in the Da Vinci Code, he did for our research work in Angels and Demons, if that helps you understand the accuracy of that, okay? But you really wouldn't expect that there would be such publicity for trying to look at the magnetism of the single electron, right? It just doesn't have the same sex appeal as this antimatter stuff, okay? And so I was really surprised to get some publicity for a paper entitled Stochastic Phase Switching of a parametrically driven electron in a pinning trap. Okay, this happened about a year ago. Okay, and we had written this paper some time ago, and it was part of this general program, and we were trying to understand the nonlinear dynamics of one-to-many electrons in our trap. And it's the most jargon-filled paper that I've ever written. Now, you've maybe heard of the actor Jim Carrey, and in our country we have a late-night TV show by Conan O'Brien. And they were busy talking one night on television, and here's what they said.
Them like that, and then they get scared. Yeah. Exactly. No, but you know, it's funny.
You're trying to feed me?
Yeah.
Amazing. Next thing you know, I'm up in the car, breaking the window.
Yeah. But you know, you're deeper than that. Like, I know you're into a lot of reading. What are you reading these days? What are you studying? What are you into?
I tell you, I absolutely love reading. I'm a huge reader. And when I pick up something, I just can't put it down, you know? Like quantum physics, that's my favorite.
Quantum physics?
Yeah.
What are you talking about? Quantum physics, like what?
was just reading this incredible paper on the stochastic phase shifting of a parametrical-driven electron in a Penning trap. Clearly, a bistability arises dynamically in this specific parametrically-driven systems because the phase psi of the electron's steady-state oscillation can either have the two values separated by pi.
These are all lines right from the papers.
But you know, it's funny. What shocks me about an electron in a Penning trap is that most amplitude collapses are accompanied by a phase flip. Given that the rate of escape from the track depends exponentially upon an activation energy E as the diffusion constant T approaches T sub n, and rho approaches epsilon with a negative E over D.
Absolutely.
Yeah,
Absolutely.
I know.
So now you're all wishing that you had read this paper, okay? Because the band leader had read this paper too, of course, right? And so he starts getting involved in the conversation, but he gets a factor of 2 wrong, so then they make fun of him, right? Just as physicists might. So anyway, that's okay. So excuse me. Let's go back to physics, okay? Magnetic moments, the motivation and the results of what we've measured. So let's start very simply, not to insult anyone, but just to make sure we're all on the same page together. A magnetic moment, the size of the bar magnet in the electron, so to speak, okay, is described by a vector, of course, because it has a direction. And if you have a simple enough system, and that system is so simple that it's described only by one angular momentum vector, then the Wigner-Eckart theorem and all that tells us that this observable must be proportional to this vector, okay? And the dimensional analysis we'll go through in just a moment says that the essential size of the magnetic moment should be the Bohr magneton, E times h bar over twice the mass of the electron, where E is the charge of the electron. And just in case we got the argument wrong, we put a fudge factor in that we call the G value. It's a dimensionless fudge factor, so we can always fix it, okay, by making it whatever size nature tells us it is. Now let's go through the simple argument in the case of an orbital angular momentum. So if we have a charge and a mass, and we're in a magnetic field, that's what this arrow represents, and the charge is going round and round in a circle. There's a radius rho and a velocity v for this charge and mass. Then the magnetic moment in SI units, as you probably know, is just the current times the area. Okay, now the current is pretty easy. There's one particle that goes around once per revolution period. Okay, so here's one charge going around once per revolution period. And then the area is pi times the area squared, right? The rho squared. And if we just multiply, cancel things out, and multiply an orbital angular momentum divided by mv rho, then we get that the magnetic moment is the orbital angular momentum divided by h bar times the Bohr magneton, just as we wrote it up here. That is to say, if the charge and mass have the same distribution in a classical system, that's generalizing my argument a bit, but it works out, then the G factor is 1. Okay? So in some sense, what the G factor tells you about is the relative charge and mass distribution in a mechanical model. Now, mechanical models are pretty dangerous when you apply them to the electron. I mean, more than that, they're wrong, okay? For example, if you say an electron is a ball, and it has charge on its surface and mass in its interior, or whatever your particular model is, and you let it rotate very rapidly, say, so its surface goes at the velocity of light, and you put the size of the electron that we know from experiments that the electron size is smaller than a certain amount, you don't get the spin of 1/2 h bar for the spin. You're 5 or 6 orders of magnitude short. Okay, so mechanical models don't work at all. On the other hand, this same basic structure does work, namely that the magnetic moment is going to go as a spin over h bar times the Bohr magneton times some fudge factor. And from Dirac theory, we get that G is not a 1, but it's 2. That's for a Dirac point particle, at least if you want to have a theory that you can renormalize. Okay? And so we're used to that. And in fact, because the electron interacts with empty space, and empty space isn't empty. It's filled with all sorts of stuff, particles appearing and disappearing, okay, as described by quantum electrodynamics. G actually is about a part per thousand bigger than that. So if we measure the G value of the electron, and that's what we do. If G is different than this value, then that would mean that there's some new physics going on, not in the standard model of particle physics. Okay, and we know of examples of that, of course. A proton or an antiproton has G which is not this value. It's about 4.48. Okay, and why is that? That's because there's interior structure to the proton and the antiproton. There's quarks inside. So if we had some quark-like things, whatever that would be, inside of the electron, then we would expect that this value would not be what we would measure. Okay? All right, so why measure the electron magnetic moment? Well, here's my reasons. The electron G is just a basic property of the simplest of elementary particles. And the electron is almost too simple, right? I mean, it seems to really be a point particle. That is to say, we have failed to detect any internal structure so far. I mean, most of us are made in large part from things that are, point particles. I mean, that's a little strange when you think about it. Okay, it turns out we can determine the fine structure constant from our measured G and QED. We can determine the fine structure constant now by a factor of 20 times more accurately than any other method. Okay, so that's sort of another consequence. If we measure G and you measure the fine structure constant by an independent method, then we can test quantum electrodynamics together. Okay? Now, unfortunately, right now, we're measuring so much more accurately that, that we, in fact, get the value of alpha from our measurements, but hopefully maybe someone in this audience will come up with a new way to measure the fine structure constant more accurately. That would really be very useful. And then we can look for new physics beyond the standard model, as I've already mentioned. Now, our result, if you just to see what we ended up with, okay, here's the expression again. This dimensionless fudge factor, the G value, well, I've normalized it to 2 because remember, for a Dirac point particle, G over 2 would be equal to 1. And so here's all of the digits. I can't remember them either, but the uncertainty is 2.8 parts in 10 to the 13. So it's a fairly accurate number right now. To compare to previous measurements, here was the famous measurement made by the University of Washington people back in 1987, about 20 years ago. Okay, and here's our 2006 measurement, and here's our new measurement, which is just in the process of being published. So these two measurements are the first improvement since 1987. There's a 15 times smaller uncertainty here than here. There's also a 1.7 standard deviation shift. Now, that's not so uncommon in the history of precise measurements, I should say. When people measure something more and more accurately and push one set of methods to a logical conclusion, it's not uncommon when someone comes up with a new way of measuring it for there to be a jump. I think that's another way of saying we humans are capable of underestimating our systematics error bars. Okay? And if you follow the muon muon magnetic moment measurements, we're now about 2,500 times more accurate than the muon values. Now that's not so surprising. We do our whole experiment in this very tiny region of space that we have very good control of. That's much easier, in some sense, than controlling the environment over a whole big storage ring, which is what has to do with the muon. Now, at the University of Washington, they're very proud of the 1987 result, of course. So they chiseled it in the outside of their new physics building, along with Maxwell's equations and other immutable objects. So when I was out there a while ago, I had to have a lunch with the students, and so I suggested to the students that as a project, they could correct the error that was in the outside of their building and chisel some new digits. Some faculty members were really unhappy with me for making that suggestion because they said, quote, "These are students, they may do it." So I'm really grateful that there's been no reported cases of vandalism at the University of Washington, and so I'm not responsible for that. Okay, so I've tried to tell you about the electron magnetic moment, what it is in particular that we're measuring, the dimensionless form, basically the magnetic moment in terms of Bohr magnetons. Now let's switch to the fine structure constant. Now, the fine structure constant is, what is it? Okay? In order to do that, I turned to Enrico Fermi to help us. And that's partly because Enrico Fermi spent a big part of his career at the University of Chicago, which is where I got my graduate degree. And he still haunts the place. At least he did when I was there. We always got told stories about how we were no match for Fermi. Okay? Now, we knew that before our professors reminded us of that, but apparently Fermi would walk around campus and analyze absolutely everything as a physicist. I mean, how would you like to be married to a guy who, analyzed everything as a physicist? Okay, it would be a very interesting situation. But the rumor was that Fermi never ever got anything wrong. Okay, and so that's why it's kind of nice to see his value of the fine structure constant. It not only doesn't have the SI units in, that's not so important, that's a matter of taste, but he actually mixed the H bar and the E, okay? So I'm very grateful to Enrico Fermi for feeling someone like me with ordinary abilities that maybe feel like I could maybe do physics as well. Now, this has been put on stamps, okay? But the politicians are much smarter than the physicists. And so here's the US stamp and here's the Italian stamp. Notice that on the US stamp they cut off the alpha equals. Okay, so that, okay, how can it be wrong if you can't see the whole equation? And then on the Italian stamp they did the same thing. Alpha equals is also cut off. So clearly the politicians were much smarter than the physicists and made sure that they didn't pervert the younger generation by showing them things that would disturb them because they were untrue. Now, we know the fine structure constant in a variety of different ways, depending on our field, okay, and I could add some here, okay, but you often see a graph like this these days. This is the energy scale for an interaction, and we hope that all the three forces that we've been able to put in the same framework, they seem to sort of unify up at some ridiculously high energy that we can't get to yet. But we spend a lot of time and effort doing that, and I'm sure some of you are engaged in that. The fine structure constant is the strength of the electromagnetic interaction at the low energy limit. Okay, that's one way to think of it. Another way is it's an important component of our system of fundamental constants. Okay, and you look in the back of your textbook and you see all these tables of constants. What you don't realize is there's a number of people who spend their whole life trying to figure out what the best value of these constants are and to try and make an internally consistent set of constants. There's even an international treaty organization which has a Swiss representative, okay, which makes decisions on these things. We're actually about to redefine the SI system of units, and I bet almost no one in this room knows that, okay? But there's a good reason for that. Right now there's this embarrassing bar of platinum, iridium, or something in Paris, right? And every 2 years they open the safe door and they look at it to see what sort of crud it's grown recently, okay? That's the mass standard for the whole world, okay? Now that's sort of insulting to all physicists, I think. So it's certainly, certainly we're past due to get rid of that. And Reinhold and his collaborators have actually made some measurements which will help with that as well. Okay, now another way to think of the role of the fine structure constant is in atomic physics. The fine structure constant tells you the scale of anything. Okay, the binding energy of an atom is alpha squared times the rest energy of the electron. The fine structure is alpha to the 4th times this rest energy. The Lamb shift is alpha to the 5th. The hyperfine structure, well, now you've got a nucleus involved, so there's an electron to a proton mass ratio, and alpha to the 4th mc squared. And one more Feynman story, okay, to add to the one in the introduction. Feynman famously said that every theorist, but I think we could expand it to experimenters as well, should put 137 on the office wall, okay, as a reminder of how little we really understand in physics, as we have no idea why the fine structure constant is approximately 1 over 137. Okay, we just don't know. Okay, so I've told you a little bit about the G value, the electron magnetic moment, which someone could measure. I've also told you about the fine structure constant, and that can be measured in various ways. Now let's connect the two, okay? And that's this theory of quantum electrodynamics, at least that's a big part of it, that was mentioned in the introduction. So how does it go? Well, here's the G value, or G over 2, which we're able to measure, and I'll show you in more detail how we did that. G over 2 is about equal to 1. That's what you'd expect for a Dirac point particle. And the electron seems to be at least close to a Dirac point particle. Then there's a bunch of terms which come from quantum electrodynamics. Excuse me. Now, alpha is about 1 over 137, and pi is about 3, so this is a couple hundred. So this seems like a very nice series, you know. I mean, if I take a couple of 100, a couple hundred squared, a couple hundred cubed and stuff, it seems to be very convergent, okay? In fact, there's a dirty secret which we don't usually like to talk about. Namely, this is believed to be an asymptotic series or worse, which means if you add too many terms, it's going to suddenly start to blow up. But that just makes us feel so uncomfortable, and we're proud of quantum electrodynamics, so we just don't talk about it, okay? And then there are some little corrections which are small enough not to be important at the current level of accuracy of the measurements, and they're due to hadronic and weak standard model contributions. Right now, they barely contribute at the level of the measurement, and the uncertainty in them is far smaller. Now, we can use this expression in two different ways. What you'd like to do is, you'd like me to measure G over 2 with my group, and then you maybe measure the fine structure constant in a completely independent way. Okay? And then we could compare, using this expression, as a test of quantum electrodynamics, to see just how good quantum electrodynamics really is. Okay? That's one method. Now, we do that, and we do that to an astounding level of accuracy. More about that in a moment. On the other hand, we now measure G so much more accurately than alpha that the way we're using this is we're putting our G value in and solving this equation for alpha, and that's how the alpha values that are in your fundamental constants compilations, that's where it comes from right now. Okay? Now here's the theorists who do it, and since I made a nasty comment about theorists this morning, for Eva's sake, I mean, I really like theorists, okay? And every experimenter wants to bask in the reflected glow of theorists, so here's me trying to do this. Okay, and Kinoshita is the guy who calculated the C4 coefficient, okay, about 1,000 Feynman diagrams, and he spent a big chunk of his life doing it. Now, when I was a graduate student, that was the term that my very famous University of Chicago professor assured our class could never possibly be calculated, okay? Kinoshita has now calculated it, and he's busy calculating this one as well. Okay, so, you know, any good student, if the hero professors say something's impossible, that means you should really prove that they're wrong, okay? And then this guy, Remedy, and his group finished off calculating this term entirely analytically, which I think was a real tour de force. Okay, it isn't celebrated so much, but that's very important as well. So, these guys, well, they're very important to our extracting the fine structure constant because we need their coefficients in order to do it properly. Okay, if we now invert the expression and solve for alpha, we're thus assuming there's no new physics beyond the standard model, and we're assuming that QED is a good description of reality, and that the QED calculation that's been done has been done correctly. Okay, those are three assumptions. Then we get the fine structure constant out that has this sort of accuracy. I won't go, this is the experimental contribution. These are two different theoretical contributions. The biggest limit right now is we don't know the C5 coefficient at all. Okay, and so we have no bound on it. And so we use only a very crude estimate in order to get this limit. That's supposed to be calculated in the next year or two. Kinoshita and Neo are busy working on that. Okay, if you take our value of alpha and compare it to the next most accurate values, these are so-called atom recoil measurements. Okay, this is one done in rubidium and one done in cesium. And these are right now about 20 times less accurate than our current measurement. Now, both of the groups who did these two measurements are hard at work trying to improve their fine structure constant measurement. Both groups believe that they should be able to improve things at least on the factor of 3 or 5 or something like that. It gets harder to get them to commit to something beyond that. But even a factor of 3 or 5 would be important because we could then immediately test quantum electrodynamics together at a higher level of accuracy. Okay. Now, just a quick thing about these other methods to measure alpha. They're not the methods that you've probably heard of because they're relatively recent. If you take the fine structure constant formula, the definition, and the Rydberg constant formula, which has been very accurately measured, as you probably know, more accurately than the fine structure constant, and you take these two formulas and mix them together, then what you get is an h bar over the mass of the electron. Well, you can't measure that so well, so instead, h bar over the mass of a cesium atom is measured. Either when cesium, it's using an atom interferometer, and in rubidium using an optical lattice. I don't have time to talk about how those measurements are done. But if those people make measurements, plus these mass ratios are measured, much like the mass ratios are measured here in Sweden, okay? So this particular one is very important. Then if all of these groups together make their part of the measurement, you can get the fine structure constant out. Now what limits the accuracy right now is the measuring of H over M for the cesium or rubidium atom. And in this business, the measurement gets named for the weakest link, okay, not the strongest link, which isn't fair, but it's the way it works. Okay. Okay, if you miss some of your favorite ways to determine the fine structure constant, they may be on this graph. I grew up with the A.C. Josephson measurement of the fine structure constant, which was the standard for all of us for many years. There's the muonium hyperfine, the quantum Hall measurement more recently. These are these two atom recoil measurements. I hate this plot because our error bar is so much smaller than the point. You know, it's sort of not fair to all the hard work that went into it. But the error bars are very big here. For reasons that aren't understood, the A.C. Josephson junction measurement just seems to be wrong. The others are fairly internally consistent. Okay? All right. Now, for testing quantum electrodynamics, what we can do is we can compare our experimental value to what you would calculate using the fine structure constant from the next most accurate measurement. Okay? And so the next most accurate measurement then is from these atom recoil measurements. If we plug in that value of alpha, use the QED theory, we test that quantum electrodynamics is good at the 15 parts in 10 to the 12 level. Okay? Now that's a good level of precision. Okay? If someone else could measure the fine structure constant much more accurately, independently, we can immediately do an order of magnitude or more better. Because right now, all of this uncertainty comes from the fine structure constant measurement. Now, this is sort of like the story in the introduction. When we were publishing this result in 2006, I put a line in one of the papers that QED had now been tested far more accurately than its inventors could ever have imagined. And the referee objected to that, saying, basically, Jerry, you're an old guy, but not old enough to know what the inventors were imagining. Okay? Well, and it's true. I hadn't talked to any of them in person. So Freeman Dyson, one of the inventors, was still alive, the only one alive. So I sent him a copy of the papers and said, Freeman, what do you think? And Freeman sent me this lovely note back, which said, as one of the inventors, and the sense of this is very much the same as the thing you put up in the introduction. As one of the inventors, I remember that we thought of QED in 1949 as a temporary and Jerry-built structure. Well, since Jerry is my name, I don't like this word choice, but okay, but with mathematical inconsistencies and renormalized infinity swept under the rug, we did not expect it to last more than 10 years before some more solidly built theory would replace it. To me, it remains perpetually amazing that nature dances to the tune that we scribbled so carelessly 57 years ago, and it is amazing that you can measure her dance to 1 part per trillion and find her still following our beat. Well, it wasn't so hard to deal with referees' objections then, because we sent a copy of Freeman's letter, okay, to the referee and said we have fixed the error in the paper by adding a reference to Freeman Dyson private communication. So may all of our referee interactions be that smooth. Okay. Now, there's a number of different things that I could go through here. Since Reinhold brought this up in my talk this morning, I'll just mention that even though 1 electron QED seems remarkably good, it's doing very well, okay? Better than its inventors could ever have imagined, I still think. If you have 2 electrons and do QED, then it's not so good, and we don't know the reason why, whether the problem is QED or whether it's just a bookkeeping problem in the very complicated atomic calculations that have to be done. But here's a number of measurements of 3 different intervals in helium fine structure. These are laser spectroscopy measurements. The details aren't so important here. Our measurement is the most accurate of these, but only by a little bit. So there's a number of different groups that have measured this at about the same accuracy. We all agree, and the theory values are way off to the side, and they don't agree very well. Okay? So that's a bit of a problem, which says all isn't well in QED land. And as you said this morning in the seminar, it's kind of a puzzlement, and I have no idea why that happens or what the story is, what to do about that. Okay, about the internal structure of the electron. If you use a model done by Brodsky and Drow, which is a fairly generic model, so it's not very specific, they say if M star is the total mass of all the internal particles that are bound together to make an electron. Okay, that's M star. And then you put it together so some binding energy comes out, right? So the particle doesn't weigh as much as it started with. The claim is that our measurement sets a limit, which is the electron mass over the square root of this delta G, the difference between the calculated and the experimental value, okay, which is 130 GeV over c squared. Okay, now that's limited, in fact, by the uncertainty in alpha. Just our uncertainty alone, okay, would let us go up to the 2 TeV range. Now, that's not such a bad energy for an experiment that's done at a small university laboratory, okay, down at 100 millikelvin, okay, because usually to get any TeV thing, you need a really big accelerator. But LEP does do better. The claim is that by colliding electrons and positrons and looking to see if any stuff comes out, okay, that the limit is about 10 TeV, so it's a little bit better. But it means that the electron is this really remarkable thing. If it has internal structure, it really seems like there's an incredible amount of binding energy. To start at 2 TeV ingredients and then bind them tightly enough together so that you're down to a half MeV of energy is a really remarkable thing. So the electron is unbelievably strange, even though we don't think about it in that way oftentimes. Okay. Someone else asked me about this today, so just let me say this. The G value for the electron there's also such an expression for the muon. It has the same structure. There's a quantum electrodynamics piece, a Dirac piece, there's a hadronic piece, and a new physics piece. And I mention that because these last two terms are expected to be about 40,000 times bigger in the muon, say, for example, if there's a new particle that we haven't discovered yet. So the muon should be much more sensitive to new physics. That means the muon is not a very good place to measure the fine structure constant, okay, but it is a very good place to look for new physics. Okay, the problem with the muon measurement is this term. The other hadronic terms not described by QED are also 40,000 times bigger. And not all of those theorists don't know how to calculate that, so they have to do awful things like integrate structure function graphs from experimenters and stuff like that, which is sort of a hard way to go. Now, the reason I mention this is because right now the measured muon magnetic moment and the calculated one do not agree at the 3 sigma level. Okay, it's the only place that we know of where the standard model seems maybe to be breaking down. Now, my suspicion is that there's probably a problem with calculating this term, but what do I know? I'm just an experimenter, okay? But in any case, people often ask us, could we measure this in the electron system and look to see if we could see this effect ourselves? And the answer is yes, but certainly no. Okay, let me explain that. The new physics is 40,000 times more prominent in the muon case. Okay, but we catch up. Well, now it's a factor of 2,500. I haven't updated this slide, I just noticed. And then there's a factor of 3. So if we improve our measurement by a factor of 5 or 10, we could start probing, the 3 sigma deviation that they see. On the other hand, that's not the whole story. Somebody also has to measure alpha, by a couple of orders of magnitude more accurately. Okay, and that's the really difficult thing. So if one of you could come up with a way to do that, then we could actually check whether this breakdown of the standard model that's glimpsed in the muon case is real or a mistake. Okay? So, okay. Now, I talked to one of you before the talk, and I understand there's a whole wing of people who understand these things. An unusual use of our measurement that's come up, and I've got another paper too, but I didn't put it up here yet. I got it from email recently. Our measurement has been used to try and help make the constraint on low mass dark matter particles. Low mass meaning electron mass-ish kind of dark matter particles. And I'd love to talk to experts about this to find out if this is a legit thing or what the story is. It certainly wasn't something that I was expecting our measurement to be used for. Okay, now let me finish off with the time by saying in a little more detail how we actually do the measurement of the electron magnetic moment. All right, I've already given you some of the ideas, but in such a terse way that I think you probably didn't follow that in much detail. And I've already told you the punchline, so just let me restate it here. Basically, we were able to make a fully quantum system, the electron bound to our apparatus in such a way that we could probe the lowest energy levels of the spin and the cyclotron motion. Okay, that's really the basic idea. Okay, now let me go through this in some more detail. So a particle physicist thinks of an accelerator sort of like this. Okay, there's a particle going round and round in a magnetic field, and if your accelerator is very big, you put a hole in the middle because it's too hard to make a magnetic field, you know, that just goes out over miles or kilometers. Okay, but for an electron in a 6 Tesla field, it would go round and round at 150 gigahertz. Okay, that's a high microwave frequency. Okay, about 2 millimeter wavelength, so that's a hard frequency to work at. Now, that particle could drift out along the magnetic field line either direction. And so what's often done is we put negative charges above and below, okay, and those negative charges persuade the electron not to leave our trap. Now this is sort of the 0th order version of what a penning trap is. And as you probably know, there are very good measurements done with a penning trap here in this department, okay? And this is the basic idea of this device. Now, normally, you know, cyclotron motion is always classical, okay? In fact, I think this is the only case really where it's not, except in the density of states in the quantum Hall system, but that's a very different story. But what we want is we don't want a big orbit where there's a circular orbit. We want to shrink down the orbit size until the orbit size is quantized and the energy is quantized. And as you all know, we get equally spaced energy levels, separated by h bar times the angular cyclotron frequency, okay, going up up to infinity. Now, our ideal system, and this is actually what we realized, we'd like the particle to start out always in the ground state. Okay, and if it was always in the ground state, then we could put photons into our system and persuade it to jump up occasionally to the first excited state. That's the idea. Now, if you're in the ground state, there's nothing going around here. In quantum mechanics, we have a special name for such a boring state. We call it a stationary state, right? Nothing happens, it just sits there. Here's the distribution of electron as you go off the center axis, and it just tails off and it just sits there, okay? And then if we go up to the first excited state, again, nothing moves still, okay? There's just another boring electron, you know, charge distribution, whatever you want to call it, okay? And so what we'd really like to do is we'd like to be down in the ground state all the time until we put photons in the cavity. Well, what do you need in order to be in the ground state? Well, you need to have this electron system in thermal equilibrium. Okay, getting one electron that's a centimeter away from everything else in thermal equilibrium is an interesting undertaking. Okay, but then we'd also like the temperature of that thermal equilibrium to be very low compared to 7 Kelvin, which is the energy spacing in temperature units. Okay, and in fact we cool way below that temperature. To do that, we use, to use that, we use a dilution refrigerator, a common device in low temperature and condensed matter physics. In my country, we use these primitive units of length, the size of some English king's foot or something, okay, and it's 8.5 of these feet, okay, and then the actual apparatus that the electron sits in is only about so big, a few centimeters on the side, okay? Now let's think about, well, here's a picture of it. Here's the long, skinny apparatus. David just got his degree. Shannon is just running the apparatus entirely on her own the last week or so for the first time. I have my fingers crossed because we're going to see how good she is. Okay, and that's going to depend on the success. The success of the experiment will depend on that the next few years. Now, there's a doer here, and then there's a superconducting solenoid doer down below the floor. This long skinny apparatus goes up through the roof and is hoisted down. It's suspended up here, and then 2 meters below hangs the electron in its trap. Okay? We're replacing that apparatus now, but I don't have time to talk about that. Now let's think about the electron in its little box. Okay? If the box is hot, then there are black body photons given off. And so black body photons will occasionally have the right frequency to excite the electron. Okay? And now the electron can de-excite via spontaneous emission or stimulated emission. Okay, now we don't like to have hot cavities with black body photons, so we cool our cavity down to 100 millikelvin or even a little below, and that essentially gets rid of the black body photons. Not entirely, but essentially it does. Okay, and so there are no excitations up. It takes about 10 to the 30 some years before there's an excitation, right? Which is long enough to do one of these experiments even. Okay, and so then spontaneous emission will take us down to the lowest state. Okay, and then we have just the state that we want to start from for our experiment. Here's some evidence of that from a few years ago. Okay, what's shown here is energy versus time. Okay, and this is energy in the cyclotron motion. Okay, versus an hour of time. And this is at different apparatus temperatures as we go from 4 Kelvin down to below 100 millikelvin. And what you see if you look is it's pretty easy to imagine after a while that the cyclotron energy is quantized. We're either in a ground state or a first excited state or a second excited state. And you see these nice flat tops. Well, there's also some little short spiky events. Okay, what's that all about? Well, what's happening there is we get an excitation, we believe, up to the first excited state, but then it decays in a time shorter than our averaging time. Okay, the averaging time that we need to get this sort of a signal from one electron with almost no energy. Okay, and so then we see these spiky events. These are just shorter than what we can resolve. Okay, now these are kind of strange states if you think about it. Clearly, as we go down in temperature, let's go down to 1.6 Kelvin, we're almost always in the ground state, and then when we do excite, about once per hour, we excite to the first excited state. So we're clearly in one energy eigenstate or another. Okay, there's different communities use different terms, Fock states, Landau levels, whatever. The point is that at 1.6 Kelvin, we only get about 1 excitation per hour. We wait a little bit of time, and then the particle decays via spontaneous emission, almost certainly. Okay, so these are, in what sense are these in the thermal state? Remember, I claimed they were in thermal equilibrium. What does that mean? Okay, well, here's what it means. If you plot the probability for being in the ground state and the first excited state and the second excited state under each of these situations, not only for the data shown here, but for many hours more, okay, then you can see that there's a probability to be in the ground state, to be in the first excited state and the second excited state. You can fit that then to a Boltzmann distribution, and that's the temperature that the electron thinks it has. Okay, and in fact, that temperature agrees all the way down to 1.6 Kelvin very well. Below 100 millikelvin, we never see the particle come out of the ground state, so we can't really measure a temperature, but then temperature doesn't really matter anymore as a concept, because if you're in only one quantum state, who cares about the temperature? Okay? So, the averaged over hours, we're in a thermal state. Now, this illustrates how quantum mechanics isn't quite as satisfying as one might like if you're doing one particle experiments. Quantum mechanics describes the behavior of an ensemble. Okay? To make an ensemble out of one particle, what we have to do is we have to take one electron and average its behavior over many hours, and that's our ensemble average. Okay? And in that sense, we get a thermal state. Okay. Let me just jump to the basic idea of the measurement here. The basic idea is that there's not actually only one ladder of cyclotron states. There are two, okay, because there's also energy in the spin. And so if I flip the spin, I can change the energy of the electron. It turns out that's about the same amount. So this is the spin precession frequency, and this is the cyclotron frequency. And the spin frequency and the cyclotron frequency are related by just this G value. So it's simple. We just solve the G value equation, okay, in terms of a frequency, a spin frequency, and a cyclotron frequency. Now, like done at the University of Michigan and then at the University of Washington, we actually measure this difference frequency to get a little higher uncertainty for free. Okay, but okay, that's an embellishment as far as the particular talk is concerned. So now, this is great to measure frequencies because there's nothing we can measure better than a frequency, okay, because the art of timekeeping is so well established. You know, generations of people have worked on that, and very successfully. The only thing we can measure better than a frequency is a ratio of frequencies, because then the clock doesn't even have to be stable except over our measurement time. Okay, so this is a good thing. Okay, now let me talk about the trap. This is the cylindrical pinning trap that we use. It's a right circular cylinder, and in the inside of this cylinder, we arrange that the equipotentials look like the inner contours of this orange contour. That's what the electron needs to have a nice harmonic oscillation up and down along the direction of the magnetic field line. Now, the right circular cylinder is very important, and like I said, this trap was invented just for this experiment, because that right circular cylinder puts boundary conditions on the radiation modes of free space. And that's what allows us to inhibit spontaneous emission. I'll say just a bit more about that in a moment. Okay. So, how do we do the detection? Well, we actually detect the up and down motion of the particle in the trap. Okay? This is not the cyclotron motion, it's not the spin motion. The cyclotron motion is in an orthogonal plane because this is going along the magnetic field. But 150 gigahertz is just too difficult to detect. And so instead we detect this motion. This is a theorist's view of what we do. I mean, it's a lot more complicated. There's a whole room full of electronics involved. But we just induce a current through a resistor we connect across these electrodes. We measure the voltage across it, and then we feed the voltage back so that we cancel out the I squared R damping losses. So we get this nice big classical oscillation of our single electron. We measure its frequency very accurately, and it turns out that small changes in this frequency tell us which state we're in. Okay, I don't have time to tell you about that in any detail, but it's a quantum non-demolition measurement, which means we get to sweep the dirty parts of our detector under the rug. Okay, the right parts of the Hamiltonian commute and that sort of thing. Okay, what do we measure? Well, here's the kind of line shapes that we see. Well, let's see, where are the line shapes that we see? Here we go. Okay. Come on, Bill. Okay. What we do is we prepare the particle in this state. We drive this transition, generally to measure the cyclotron frequency. The experiment is simple. We try 100 times to make an excitation at one frequency, and then we plot what fraction of the successes we get at that frequency. Then we move the frequency and we try it again. So it's quantum jump spectroscopy at its very simplest. We do the same thing, preparing the particle in this state and then driving the anomaly transition. Okay, and then if we make this transition, then the particle spontaneously emits a photon and drops to the ground state, and we see the spin flip. Okay, and so again, we get a nice line shape from that. Now the shapes are fairly well understood, not perfectly, okay, but I don't really have time to talk about them right now. A couple of interesting features of the system. When the subway goes by, it changes the magnetic field in the lab. Okay, that's a big perturbation for us, even though the subway is 100 meters away. But we have a solenoid that has a self-shielded coil built inside, something we patented some years ago. And so when the subway goes by, an extra current is induced in the solenoid to cancel that out. That's now being used in MRI imaging. You never know about these applications because it lets you put your MRI imaging machine nearer to an elevator, for example. Here's a big mistake that I made. I forgot about the nuclear paramagnetism of copper. And so as we went down to very low temperatures and we changed the temperature, the electrons saw a magnetic field that was varied in a very characteristic way. And only then did I remember that low-temperature physicists use that nuclear paramagnetism for thermometry. Okay, it was in a different lobe of my brain, but the two lobes weren't wired. It cost my student a year because we had to throw the whole apparatus away and build a trap out of silver with a titanium. We had to get rid of all the nuclear spins. Okay, another interesting feature here is, let me see if I can find it since I really... is we can measure the inhibited spontaneous emission. You see these lifetime, or these quantum jumps, if we jump up to a certain state, we can now make a histogram of how long we spend in the excited state. Okay, and we can directly measure the lifetime of that quantum state. Here's the histogram, and we get a nice exponential decay, which is 16 seconds long. Now, if you calculate that using classical radiation theory or quantum electrodynamics, you get the same result, so it's probably right. You get that it should be 75 milliseconds. So we've inhibited spontaneous emission by a factor of 210. Okay, that's where that cylindrical penning trap comes into play, because the density of states inside of a box is different than the density of states that you get when you take the box and let the walls go to infinity, as we do typically in a physics problem set. Okay? And so the density of states is lumpy here. We choose the magnetic field so that the cyclotron frequency is as far away from where there's a big density of states as possible. Okay? And that way the electron looks out and says, boy, I'd like to radiate a photon today, but there's no density of states, and so it doesn't. And that gives us the time that's required to average and detect this really tiny signal from one particle that's making only a one quantum transition. Okay, let me jump then to a conclusion, okay, because time is running out. Come on, Bill Gates, you got to let me see the slides here. Okay. Okay, how do we measure to 7.6 parts in 10 to the 13? I've tried to give you the flavor. I've swindled you a bit, of course, because this isn't so easy to do. We've been working at it for 20 years, okay? And so, but in a 1-hour summary, you know, I have to swindle you a bit. I've tried to swindle you honestly. There's all sorts of different methods that are used, and we've developed them one thesis at a time. Okay, the point here is that you can't measure a fundamental constant these days and do it substantially better than it's been done before without developing some new methods, so you just have to pay your dues. There's really no other way to do it. Okay, so our new measurement of the electron magnetic moment has an accuracy of 2.8 parts in 10 to the 13. It's about 15 times more accurate than the value that stood for 20 years, done by Damelt and company. Okay, there's also a 1.7 standard deviation shift. We're able to determine the fine structure constant from this measurement. I won't show you the slide again, but we're able to determine the fine structure constant about 20 times more accurately than any other method, though I hope someone who's young and in this room will improve on that. So here's my final slide. I think that we can actually do somewhat better. I mean, that's going to sound a little strange after 20 years, but we've really only been making measurements where we put all these different methods together for a couple of years now. And we're still learning how to do that. Plus, we're also trying to learn how to take this up and down motion along the magnetic field and cool it to its quantum ground state. And I think we have at least some possibility for success as well. So it may be that we can do a little better. In addition, there are some spin-off measurements. We're right now trying to compare the positron and electron G-factors to make the best test of CPT for leptons. We think we should be able to improve the lepton CPT test by about a factor of 15 or 20. We've recently put one proton in a trap, and we're trying to see a one proton spin flip. Now, seeing a proton spin flip is a lot harder than seeing an electron spin flip, because a nuclear magneton is a lot smaller than what a Bohr magneton is. Okay, so I don't know that we're going to succeed, but if we do, we should be able to measure the antiproton and proton magnetic moments and compare them at an accuracy about 1,000,000 times better or more than what they've been compared so far. And we think that some of these methods could be used to measure the proton to electron mass ratio directly without relying on heavy atom QED. So it's kind of exciting, after 20 years of working hard on this experiment, not getting much recognition for it, finally it did work, and that's always great if you're going to invest that amount of time. And moreover, there's these nice spin-off measurements, all of which can be done in a university laboratory by a professor and a couple of students. So we think that the next few years should be a lot of fun as we build on 20 years of hard work, and we're looking forward to them. Thanks.
Wonderful talk. Do you have no questions? Yes?
Yeah, I think you showed us some line shapes.
Yes.
You mentioned that to understand them much fully.
Yes.
I was curious, is the shape understood, the parameters not understood?
Okay. Let me tell you the story. Basically, I was running out of time. I think I'm not talking as fast as usual because I have almost no voice left, okay? But in order to detect the particle and make a coupling between this up and down motion and the cyclotron motion, we put a very small gradient in the magnetic field so that as the cyclotron orbit gets bigger, it samples a little different magnetic field. Now, you can't really understand the details of that, okay? But that gives us our detection possibility. You can't understand the details given the length of the explanation, okay? But the flip side of that is that our cyclotron frequency is coupled to the up and down motion, thermal motion along the magnetic field direction. Now, during the sensitive parts of our experiment, we actually turn off the strong drive, the self-excited drive, where the particle drives itself, so that we have, you know, as close to darkness as possible, right? Nothing's happening to the electron when we're trying to excite it. Then after we excite it, then we turn on the detectors to see if it's been excited. Okay, now the residual thermal motion, which is only at of order 200 to 300 millikelvin in our apparatus, okay, then it makes a kind of Boltzmann distribution, which you could see in one of those resonances more than the other. It sort of looked like a Boltzmann distribution. Okay? And now you can do the theory. A guy named Lowell Brown, who I've written many papers with, worked it out some years ago. The Brownian motion, he thought that was really nifty because he wasn't the original Brown, but okay. But the Brownian motion line shape is well understood. Now, what's limiting our last measurement in accuracy is when we look carefully at the line shapes, we don't quite see that line shape. We see what's consistent with a Gaussian broadening of the line shape. Not very much, just a small fraction of the line shape. Okay, and that's the part that's not understood. So the basic features are understood. We increased our error bars just because we don't, we're not comfortable with the fact that we don't understand why it doesn't work exactly, and that's something that we want to study in the next graduate student, thesis. Okay.
Can I ask a question?
Absolutely. Some student has to ask the question too, right? It's the rules. Yeah.
You know very well that the bound electron G factor, electron bound in atom, is reduced.
Yeah.
By the binding. Only the free electron G factor is 2 plus C1 and so on. But here you have electron bound as well. Electron is not really free.
Yeah,
it's bound in your cavity, and you observe it for a long time. So how is that included in the theory? When you have to...
Yeah, let me say something about that. It's a very good point. I mean, we're trying to measure, if I can just restate the question a bit, we're trying to measure a property of a free electron. Okay, there's not enough time to do a measurement of this accuracy with the electrons free, so we bind it. Okay? Now, of course, the atom that we make, our homemade atom, is much less strongly bound than in a hydrogen atom. Okay, so instead of using one proton, we use a whole apparatus, okay, but it's a centimeter away from our particle. So the art of this is to bind it weakly enough so that those effects don't matter. Let me give you an example of one effect that might, and then assert that it doesn't. If you have a cavity like this, then when you calculate the G value using quantum electrodynamics, if you do that in a Fourier decomposition form, so look at each Fourier component, what you could worry about is that you're cutting off the low frequency modes. So the low frequency contributions to the QED, okay, would be different. So that would be one example of the sort you're measuring. And about 15, 18 years ago, several papers appeared in Physical Review letters claiming that that was a problem, okay? And my colleague Lowell Brown, who's a QED expert, looked at that and snorted and said, oh, these guys, they published something that's not even gauge invariant, and he made a snide remark, okay? And then he and some others looked at it, and they claim that, in fact, the low Fourier components just contribute way too little, okay, so that those that we do cut off make a difference. There's also a kind of Lamb shift. All the cyclotron levels are shifted, okay, but all the levels are shifted the same, okay. So as far as we know, there isn't such an effect. Now, of course, if you're in my position, you always have nightmares about that there may be something that you haven't thought of or you've forgotten, but you know that from your own measurements. Okay, you always have the nagging doubt that maybe there's some systematic uncertainty or something you've forgotten. I can't promise you that we didn't do that. All I can say is, you know, the effects that we could know about, think about, and test by turning every knob we could think of, okay, we couldn't find a problem at the current level of accuracy. Some student has to ask a question, right? Somebody who wants to be a postdoc someday. I'll remember you. Nobody wants to be a postdoc with me. These are way too hard. You might be stuck for 20 years. I understand. No more questions? I'm sorry if it wasn't clear enough, but so.
Oh, it was very clear. It was very nice. So, thank you again.
All right.